Hello everyone. In this video we will be discussing an introduction to work. Alright, so first, what is work? Well, we're going to be in the position where we apply work in a straight line, so along some axis. And if force is constant, then work actually has a very simple formula. So in that case, work is simply force times the distance that you're applying that constant force. Okay, so if you're just, pushing something along a frictionless surface, if you had a weightless rope and you were lifting something, then this would apply. However, that's usually not applying. We're usually applying a non-constant force. For example, you could be lifting up your backpack from the ground and you're going to require more force to pull it up that first, few inches than you are the last few inches to put on your back. So let's talk about what we do when force is not constant. Okay, so in this case, we could have some force function. So if we're applying our force along an axis from x equals a to x equals b, then we actually get an integral from a to b of our force function with respect to this variable x. So, it need not be horizontal here just because we see x. Absolutely could be lifting. X is just a variable. This is the formula, but why does it work? So let's check it out through an example. All right, so let's look at this example. So here we're going to be given a fully extended cable of 150 feet in length, weighing 2 pounds per feet. So you just go ahead and draw a picture. It's usually going to help here. So this is 150 feet. And we want to know how much work has been done after winding it up 50 feet. So basically we want to go, from winding up 0 feet at the bottom to 50. Okay? So how do we compute the work? Well, again, we want to think force times distance, roughly, except for our force here is not constant, right? So let's first define a variable. So let x be the amount of cable that has been wound up. Right, so x is going to start at 0 when we haven't wound any of it, and it's fully extended. And then as we wind more, the cable is going to be shorter, and we are going to be requiring less force. So, for instance, what is force at 0 when we haven't wound it up at all? Well, then it's just 150 times 2. It's 300 pounds. Right, and then if we lift it up a foot, well, then it's 149 times 2. Now it's only 149 feet in length, 2 pounds per feet. So we've got 298 pounds. And then, for instance, at the last moment here that we care about, when we have wound it up 50 feet, we're going to have 100 times 2, or 200 pounds of force. So we see that it's clearly not linear. The more we lift it up, the less force that we're applying. But how do we calculate work here? So the idea is basically, okay, I choose some x, and then I'm worried about my force at this time, right? And I'm going to lift it. We're really going to think, we're going to move it over a very, very small distance in which it is constant in terms of approximating the work done. So think force f of x applied over the distance delta x. Well, this is exactly how you're getting a Riemann sum, right? So we've got this delta x, this small change in x, and we want to think of a constant force applied across that. And so basically we're just adding up these force times distances for constant force over these little small intervals to add up to our total work, right? And so how do we end up getting the overall integral? Well, this is exactly a Riemann sum. So what we're really talking about here is the integral from 0 to 50, because our x is going from 0 down here to 50 up here, of f of x, which we'll worry about that formula in a second, dx. And the dx is just coming from this delta x, right? So this is the distance you're applying it over, and as you take smaller and smaller little lengths there, then this is our dx. So the last question really is, what is our force function, right? And so here we have a fairly simple formula, and we can kind of see what's going on from these examples that okay, we went down 2. If we had done it again, we go down 2, and after 50, we've gone down 100. basically we have this constant slope because every foot that we go up, we're going down 2 pounds. And so our f of x here starts at 300 when x is 0, and then every time x goes up 1, the force goes down 2. So it's 300 minus 2x. And thus, to get the total work, we're going to have the integral from 0 to 50 of 300 minus 2x dx. And we can go ahead and solve this pretty fast. So this is 300x minus x squared from 0 to 50. And so we get 15,000, 300 times 50, minus 50 squared, which is 2,500. And thus we get 12,500. And then what is our units here? So again, this is force times the distance. Our force is in pounds and our distance is in feet. So these are foot-pounds. Okay. All right, so now let's look at one more here before I give you an exercise. So we'll have a cylindrical tank. Again, we should draw a picture. So a cylindrical tank with radius 5 feet and height 10 feet. So this here is 5, our height is 10, and it is half filled with water. So up around the 5-foot mark. So we've got some water in there. And we want to know how much work would it take to pump all of this water over the top of the tank. And we're given the fact that the density of water here is 62 pounds per cubic foot. Okay, so our instinct should be, again, this is somehow going to become an integral. But in this case, it's not immediately obvious what our force function is or the distance that we need to pump it over. So first, let's worry about our distance. So let's use the variable y in this case. So if I am just looking at height y, somewhere between 0 and 5, right, because it's filled up to halfway, then how far does this have to travel to get out of the tank? Well, this is going to be 10 minus y, right? Because the overall height is 10, and we've already gone up y, so it's got 10 minus y remaining. So this is going to be our distance that it's got to travel. But then we need to worry about, like, what is the force on this small sliver around y, right? So what is force when all we're given is density? So you can tell here, if you don't remember from, maybe physics in the past, you can kind of look at the units to check, right? So density is in pounds per cubic foot. Force should be in pounds. And so we're looking for volume, and that is indeed true. So this is going to be the density times the volume. So we've got the 62.4. That's not a problem. So then what's the volume? Well, the basic idea here is let's zoom in. So what shape are we working with? We're working with really like a small cylindrical sliver here, right? So this is going to be delta y in height. That's how thick this cylinder is. And then we know what the area is in order to get the volume as well, right? Because we're just looking for pi r squared h. Well, our h is the delta y, and we know that our radius is 5. And so my volume here of this little slice is going to be 25 pi times our delta y. And thus force, being density times volume, is 25 pi delta y times our 62.4 from the pounds per cubic feet from our density. Okay, so what do we end up with? Well, our delta y is going to be our dy, and our integral in this case for the work, well, what y values do we care about? Well, y is 0 at the bottom of the tank, and y is 5 halfway up. So we're going from 0 to 5. And our force times distance in this case, again, the delta y becomes our dy. So we're just going to have 25 pi times 62.4, all times 10 minus y for the distance, dy. Okay, and so this one I'm just going to set up. You could figure this out. It's not too bad of an integral. So now I'm going to go ahead and give you a chance to practice one like this. All right, so for your exercise, I want you to suppose you have a 5-foot tall cylindrical tank with radius 2 feet, filled with 3 feet of gasoline which has density 45.93 pounds per cubic foot. And then you should compute the work necessary to pump all of this gasoline to the top, just like in the previous problem. All right, thank you for watching.